Hello, everyone, and welcome to Lecture 23 of Computer Architecture. Today we're going to talk about the control signals that control the data path. Last time we started part 3 of the course, where we will be talking about how we use what we learned in the logic design part about building logic blocks to build a processor that executes the instructions defined by the instruction set architecture that we learned in part 2. And this part is called microarchitecture. It's kind of the implementation of the instruction set architecture. We said that the instruction set architecture determines instruction count, but the CPI and the cycle time, these were the three factors of performance that we talked about at the beginning of the course: instruction count, CPI, and cycle time. We said that the CPI and cycle time depend not on the ISA, but on how the ISA is implemented, on the actual hardware. And we said that we're going to be looking in this course at two implementations: a simple one, which we started last time, and then a more realistic one, which uses pipelining as an optimization. And we said that to keep things simple, we are going to be focusing on a subset of the MIPS instructions, which is these instructions shown over here. And what we did last is we looked at how to start building this data path. A data path is basically a set of blocks that process addresses and process data and addresses in the CPU. And it has various components, and we saw how we put these components together to build a data path like this. Now, last time what I did is I focused on how the data itself is navigating through these different logic blocks. And what we're going to do today is we're going to repeat the same thing we did last time. So we're going to go back and start from scratch and reconstruct this data path. But this time, what we're going to focus on is the control signals. So rather than focusing on the data that was flowing between the different logic blocks, we're going to focus on the control signals and what each control signal does. Okay, so we're going to reconstruct this diagram that you see over here from scratch with some more detail. But before I start, does anybody have any questions about last time? Okay, well then let's start today talking about the data path control signals. So these control signals in blue that we saw, how they control the data path. So I'm going to start over, and we said that the first part of the data path is the part responsible for instruction fetch. And we said that this part is composed of a program counter, which contains the address of the instruction that we're currently executing. And what we're going to do with this program counter is we're going to provide it as an address to an instruction memory so that we fetch the instruction that we want to execute. And we're also going to increment it by 4 so that on the next cycle, we will execute the next instruction, unless, of course, we have a branch or jump instruction, which we will deal with later. But assuming we don't have any of those, we're simply going to increment the PC by 4 so that on the next cycle, we read the next instruction. Now, one thing to note here is that the instruction is 32 bits. Okay, we said that in MIPS, every instruction is 32 bits. And we will use these 32 bits of the instruction. These 32 bits are divided into different fields depending on the instruction format that we are using. And we're going to see today how we're going to use these different fields inside of our data path. Okay? After we fetch the instruction, what do we do with it? If we are going to execute an R-type instruction, so if you have an R-type instruction, like add or subtract or set on less than, what do we do with these 32 bits? Well, let's remember what was the format of R-type instructions. So the format of R-type instructions was like this. We have an opcode, which is 6 bits, bits 31 to 26. We have a source register, 2 source registers actually, RS and RT. We have a destination register. We have a shift amount, but we're not going to do shift instructions in this pipeline, so you don't have to worry about the shift amount. And then we have the funct code, which tells us more about the operation that needs to be performed. So what's the first thing that we do if we have an R-type instruction? Something like add, right? What does add? If I have an add instruction, what does it do? Right, so like you guys said, the first thing that we do is we read the registers. Okay, the first thing that we do is we read the registers. Now, let's go into a little bit more detail about what are these lines that are signals that are coming in over here. Okay, so and with an R-type instruction, what's read register 1 going to be? Which bits of these 32 instruction bits are going to go into read register 1? Right, exactly. So we have in the instruction format, our two source registers are RS and RT. So then the two fields that we want to provide to read register 1 and read register 2 are RS and RT. So here the instruction bits are 25 to 21, which are RS, are going to be read register 1, and instruction bits 20 to 16, which are RT, are going to go into read register 2. So we're going to use the source register numbers. The source register numbers we're going to provide are going to be extracted from the bits corresponding to RS and RT in the R format. Okay? Okay, great. So the next thing that we do with an R-type instruction is, we provided the register numbers. Now we're going to read the data. What do we do with this data now? This was an add instruction, for example, or any R-type instruction. Or most of them, I guess. What do we do with the result? Right, we pass them to an ALU. So we're going to pass these values to an ALU. How do we decide what this ALU does? Well, we're going to give it a signal. There's ALU operation signal, and this ALU operation is going to specify the operation that the ALU needs to do. Okay, so all the control signals in this diagram are going to be written in blue, and I'm going to stop at each control signal and kind of talk about what it does. So here, our first control signal of interest is ALU op, which is going to specify the operation that the ALU will do. Okay. Now we'll talk later about how we determine ALU op. But now, after we do the operation, we have the result of the operation. What happens next? Right, we need to write back the result, exactly. We need to write back the result. So we're going to take this value and we're going to bring it around and we're going to write it back to the right data. Okay, we took the output of the ALU, we brought it around and we provided as to the right data. Okay, and of course, we have another control signal over here, reg_write. And reg_write is going to specify if the instruction writes to a register or not, because not all instructions write to registers. For example, branch instructions don't write to any registers. Store instructions don't write to any registers. Jump instructions don't write to registers. So not all instructions write to registers. We want to make sure to only write to the register file if the instruction is supposed to write. And this is what this reg_write control signal does. Okay. Also, we need to provide the right register number, right? And the number of the register that we need to write to, we're going to extract that from the instruction. And which specific fields from the instruction are we going to extract and provide as the right register number? Right, so the RD is the destination register for R-type instructions. So we're going to extract bits 15 to 11, and we're going to provide those as the right register, exactly. All right, so this over here covers R-type instructions. Let's move on to the next type of instructions. So like I said, the destination register is extracted from the RD bits. Okay, let's move on now to the next type of instructions we care about, which is immediate instructions. So what format do the immediate instructions use? Right, they use the I format. Immediate instructions use the I format. And that looks something like this. The I format, we have the operation, we have RS and RT, and we have the immediate value. Okay, RS is already provided, these bits 25, 21 are already provided as the first, at read register 1. So we're going to get the value in RS at read data 1. But what we would like to do is we don't want to add the value of RS to the value of RT. We want to add the value of RS to the immediate, and we want to put the result in RT. Okay, that's what we want to do for an immediate instruction. So I'm assuming here it's add immediate, for example. So to do that, we get RS over here, but what we would like to do is we would like to do an operation between RS and the immediate value. So what we did last time is we took the immediate value, we passed it through a sign extension to make it 32 bits, and we passed it through a mux, where this mux selected the second operand of the instruction to be either the register in case of R-type instructions, or to be the immediate value in the case of immediate instructions. Okay? So now here we have another control signal of interest, which is ALU source. ALU source is responsible for selecting either the register or the immediate, depending on, so they're just selecting the register or the constant, depending on what the instruction is. Okay? Okay, so we said that we're going to select between the register or the immediate. Which bits over here of the instruction? Which here we said we're taking 16 bits from the instruction. Which specific 16 bits of the instruction are we going to use for the immediate? Right, 15 to 0. So here the immediate field are bits 15 to 0. So what we're going to do is we're going to use bits the instruction bits 15 to 0 over here and pass those to the sign extension unit so that we can get the constant that we would like to do the operation with. Okay, so the constant is extracted from the immediate field. Okay, any questions so far? Okay, so one other thing that we need to be careful about with immediate instructions is that we have the source register and an immediate value, and then the destination register is RT. However, what we provided with R-type instructions as the destination register were bits 15 to 11. So these are the bits provided to the write register. However, are these the bits that we would like to, do these bits represent the destination register for immediate instructions? They don't. What bits do we want to use as the write register for immediate instructions? Right, we want to use the RT bits. So we want to use bits 20 to 16. So what we need to have over here as the write register value is we need to have a multiplexer that selects between either bits 15 to 11 if we have an R-type instruction, or bits 20 to 16 if we have an immediate instruction. We're going to put a mux over here, and we're going to have a control signal called reg destination, and reg destination is going to specify whether the destination register for this instruction is going to be RS or if it's going to be RT. Okay, and this completes our support for immediate instructions. Yes, question.
Sir, how do we select, it's R-type or I-type?
Okay, so we're going to look at this later. So for now, just assume that we are able to select the right control signal for each structure that has a control signal. But obviously, what we're going to need to do is we're going to need to figure out what the instruction is. And how are we going to figure out what the instruction is? From the opcode, right? So the opcode tells us what the instruction is, and from the opcode we will know based on the instruction what the value for each of these control signals needs to be. Okay. And
okay, thanks.
Yeah, you're welcome. Okay, great. So now we have support for immediate instructions. The next instruction that we would like to support is the load instruction. So what format does the load instruction use? Right, the I format. So the I format looks like this. We have the opcode. We're going to have RS, which is going to be the base register. We're going to have the offset, and we're going to have RT, which is going to be the destination of the load. Okay. Now, so what we want to do is we want to add RS, or the value in RS, to the offset, and we already have support to do that. The RS bits are provided here, so we get the value of the base register over here. And then we have the offset coming in from here, being sign extended and then being selected by this mux. And we add the value of RS to the offset, and we now get this result. Okay. Now, the difference with load, though, is that we don't want to store the address. What do we want to do with the address? Right, we want to use it to load a value from memory. So we're going to take this address and we're going to pass it to a data memory. We have another important control signal here, which is memRead. So memRead is going to specify if memory is read or not. Now, why is this important? It's important because over here, I'm providing an address for the memory to read. Now, if this address is invalid, the memory is going to cause some kind of error in my CPU, correct? So I only want to read if this is actually a load instruction. If it's not a load instruction, I could have anything over here. I could have the result of some random addition or some random AND operation. I don't want to use that as an address and read from memory with it. And that is why I need a control signal to say whether or not I would like to read on this cycle. So we have this control signal memRead that tells the memory whether or not to read. And if we're doing a load instruction, we're going to set this to 1. We're going to read. We're going to get the read data over here. Now what we would like to do is we would like to take this read data and write it back. And what did we do to write it back last time? Well, what we needed to do is we needed to select, because for some instructions, we're going to write the output of the ALU. For other instructions, we're going to write the output of the memory. So what we need is we need to have a multiplexer that's going to select either the output of the ALU or the output of the memory as the value to be written back. Okay, and we have a new important control signal here, which is mem2reg. And here mem2reg is going to be used to specify if we want the memory or the ALU output to be written back. Okay, so if mem2reg is 1, it means we want to write from memory to a register. So we're going to select the output of the memory. If mem2reg is 0, it means we want to write from the ALU to register. So we're going to select the output of the ALU. And of course, the load instruction writes to RT, similar to the immediate instructions, but we already have support for this. We already have support for passing RT as a destination register. So the load instruction will set our reg destination to 0 to make sure that we write to RT, and not because there's no RD in this format. Okay, any questions? Everything's clear? Okay, so next let's move on to store instructions. So someone's asking, we are multiplying the offset by 4, but how is it done in the CPU? So actually, the CPU in the load instruction, the CPU doesn't multiply the offset by 4 for load instructions, right? When you write the load instruction, right? You're supposed to provide an offset that is a multiple of 4 if you're doing load work. Okay, that's different from the branch. In the branch, the offset's not multiplied by 4, the hardware multiplies it by 4. But with the load instruction, the offset if the offset needs to be multiplied by 4 if you're doing a load word. It needs to be a multiple of 4 if you're doing a load word.
Sir, but it's like the instruction is like something, it's if we say an array A, it's A8. Handwritten, we are multiplying 8 by 4. But how the computer reads this A8?
Right. So I just answered that question. So if the code says A of 8, you provide the computer with an instruction that has an offset. So if A is an array of integers and the high level code says A of 8, right? You want to load A of 8. Then the instruction that you provide to the computer in the offset field will not put 8. It will put 8 times 4, which is 32.
Oh, okay. It's by default, yeah. It's by default.
The correct way to generate code for A of 8 is by providing an offset of 36 in the instruction.
Oh, okay.
Right, so the CPU is not going to multiply your offset by 4 for load and store instructions. You have to do that yourself. Okay, or the compiler or whoever's.
The compiler, does it by default.
Of course, otherwise the compiler wouldn't be generating correct code, right?
Okay, yes, thanks.
Compilers generate correct code. We trust them to do that. Otherwise, everything we're doing would be meaningless. Okay, so moving on to store instructions. With store instructions, what format do they use? What format do store instructions use? The I format, exactly. So store instructions use the I format, okay? And so what the store instruction needs to do is that it needs to add RS and the offset. So we already have a way to do that, right? We have the RS bits coming in from here. We get the value of RS over here. And then we have the offset bits coming in from here. They get sign extended, and then they get selected by the ALU. And this is how we add the value of RS to the offset to get the address we want to store to. And now we're going to pass this address to the memory. But now what we would like to do differently for the store instruction is that we're not, the load instruction gets a value from memory and puts it in RT. What the store instruction is going to do is that it's going to get the value of RT and it's going to store that in memory. Now we already have support for getting the value of RT, right? Because RT is provided over here as an input. So we're going to get the value of RT over here at read data 2, correct? We already have the hardware in place to get that. So what's left is taking the value of RT, which I have over here, and passing that as the write data, and that's exactly what we do. So we're going to take the value of RT from here, and we're going to pass that as the write data. And of course, what we need is a memWrite signal. And this memWrite signal is going to specify that memory is being written. And this is very important because if we don't have a store instruction, we don't want to write anything to the memory. And that is why we need to tell the memory whether or not to write. Because if we don't do that and we just let it write every cycle, then if I have an add instruction, the second input is going to be RT, is going to take that's going to be taken and written to memory. And we don't want that. We only want to write on a store instruction. And that is why we're going to have a memWrite signal to tell the data memory whether or not to write. Okay? Clear? Any questions? Okay, well, next we looked at branch instructions. So what format do branch instructions use? Right, they also use the I format. So a branch instruction looks like this. They use the I format. We have RS and RT, which are source registers, right? So RT is a destination register for load and for add immediate, but it says source register for store and for branch, okay? So RS and RT are two source registers, and this offset is what we will use to calculate the target address. And we know that branches use PC relative addressing, so the target address is going to be PC plus 4 plus offset times 4. Now, what the branch instruction needs to do is it needs to compare the values of RS and RT, and if they are the same, we want to, assuming this is a branch if equal instruction, if they're the same, we want to branch the target address. Okay, now we already have hardware support for comparing RS and RT, right? Because here we have the bits for the bits for RS are coming into read register 1, The bits for RT are already coming in to read register 2. So we already have the values of RS and RT out here. If we set ALU source to 0, we get the values of RS and RT at the ALU. And if we set ALU op to subtract, then we're going to subtract RS and RT. And if they are equal, we will get this 0 flag set to 1. Okay, which means that we need to take the branch. Okay, so we already have support for comparing RS and RT and getting a flag that tells us whether or not the branch should be taken. What we also need to do is we need to take the offset, which is bits 15 to 0, which is already coming in from here. And we would like to take this value and use it to calculate the target address using this technique over here, PC plus 4 plus offset times 4. So we're going to take this value of the offset and we're going to bring it up and we're going to pass it to an adder where we're going to do the offset times 4 by shifting left by 2, and then we're going to add it to PC plus 4. Okay, and we're going to get the target address at the output of this adder, and then what we're going to do is we want to either select this value PC plus 4 plus offset times 4 as the target address, or we want to select PC plus 4, right? We'll just go on to the next instruction. So that's what we have the mux here for. And the question is, when do we select the branch target address, and when do we just select PC plus 4? Okay, so obviously it's going to have to involve the 0 bit, right? But can I just pass the 0 bit directly? So obviously, if the 0 bit is 1, it means that these two values were equal, assuming I'm doing a branch. But can I pass the 0 bit directly here? What if this was an add instruction? Or what if this was a load instruction, right? Or it could be all kinds of things, right? I only want to branch if the two operands are 0 and if this is actually a branch instruction, right? If it's not a branch instruction, then I don't want to branch. I always want to take PC plus 4, correct? So what do I need to do? So we're gonna pass in here. We have two conditions to select the branch target address. What is that? If it's a branch and if the result of the ALU is 0. So we're gonna have an AND gate over here. You guys remember AND gates? Yeah. So we're gonna have an AND gate, and the AND gate's gonna take two input values. We're gonna have a control signal called branch, which specifies whether or not the instruction that's executing is a branch. And we're going to take in this 0 bit over here. Okay, and then this 0 bit is going to specify whether the two values are equal because the result of the subtraction will be 0. So if this instruction is a branch and the output of the ALU is 0, then we will select 1 over here, which will be the output of this circuit that does offset times 4 plus PC plus 4. Otherwise, we're going to select PC plus 4. Okay? Clear so far? Any questions?
Sir?
Yes.
I was asking that إذا كانت نحن we're not using a branch, 0 isn't supposed to be 0 equal to 0?
If we're not using a branch, then this branch value over here will be 0. So you will never, you always select the value on top. It doesn't matter if the output of the ALU is 0 or not, right? Because if it's not a branch, it could be an add instruction. The result of the addition is 0, right? But that doesn't mean you should branch.
But what I mean, no, without the AND gate. I was speaking إنه the 0 وإذا عملنا لها connection دغري على multiplexer, isn't it supposed to be here equal to 0 if it's not إنه a branch equal instruction?
No, because the ALU, this zero will be set if the output of the ALU is 0, right? Regardless of what the instruction is.
Okay, thank you.
Right? So remember how when we implemented this ALU, what we did to get this 0, we just had a big NOR gate, and we gave it all the bits. And if all the bits were 0, then this flag will be 1. Otherwise, it will be 0. Remember that?
Yeah, all right. I thought it's بس خاصة بالبرانش. Okay, thank you.
No, it's not specific to the branch.
Okay.
Okay, other questions?
What if it's greater than if it's greater than or equal, it will be 0, and if it's less than, it will be 1, right? But
No,
you need
this is not set on less than. Okay, we're not doing set on less than here. So we're not looking at the we're doing is we're using subtraction, and we get a flag that's going to be 1 if the result is 0, and
yes.
Yeah,
Sorry.
two different things. Yeah, I think you're thinking about set on less than. Okay, so this covers branch instructions, and this is now the data path that we constructed last time, but now with a little bit more detail about what are we using each of the instruction fields for, and what each of these control signals do. Now the question is, how do we determine all these control signals? Okay, and the answer is in the title, right? There's a control unit that does that. So we have a main control unit, right? So all these signals, all these blue signals that are scattered around the circuit, we're going to take these lines and we're going to have a main control going to output all these lines, right? Except ALU op, which I'll talk about later. All these lines are going to be determined by the control unit. And the control unit, how is the control unit going to determine these lines? Well, obviously the control unit, to determine these lines, needs to know what the instruction is, right? Because these lines depend on the instruction. Okay, so how do we know what the instruction is? How does the main control unit find what the instruction is? Exactly, the opcode. So so what does the control unit need to know? It needs to know the opcode. Which bits of the instruction give us the opcode? Right, exactly. So we're going to use bits 31 to 26, which are the opcode. We're going to take those and we're going to feed them to a control unit. And this control unit, based on these bits, is going to figure out these control signals and send them to all the different structures. Okay? And this is kind of part of decoding the instruction, figuring out what the instruction is and generating the corresponding signals. You're absolutely right. So someone is asking, but isn't funked, don't we need to use funked sometimes? And that is correct. So the cases where we need to use funked are all related to the ALU. Okay, so with these other instructions, reading or writing to the memory, reading and writing to the register file, whether it's a branch, whether it's a jump, we don't need funked for that. The opcode is enough for that. The only one that we cannot determine from just the opcode is what? It's ALU op. Okay, and that is why I didn't connect ALU op directly to the control unit. What we're going to do is for ALU op, we're going to have an ALU control unit. Okay, so here the opcode is not enough to determine the ALU operation. So what we're going to need to do is we're going to need to have a special controller for the ALU. We're going to use a special control unit for the ALU. Okay, and what is this control unit going to need? What does this control unit need as an input? It needs funked. Obviously, going to need funked. Is funked enough? Right. It needs both it needs both the opcode and the funct, or it needs to know the opcode and the funct. So what we're actually going to do is we already have the opcode coming to the main control unit. So what we're going to do is we're going to have the main control unit decode the opcode, and based on that, it's going to tell the ALU control unit what to do. Okay. Now, if the instruction is not an R-type instruction, meaning it does not have a funct field, then the main control unit can already determine what the operation should be. So for example, if the instruction is a load instruction, the main control unit knows that it's a load instruction from the opcode, so it knows that the ALU needs to perform an addition. So it's going to tell the ALU control, hey, perform an addition, and the ALU control will tell the ALU to perform an addition. If the instruction, for example, is branch if equal, right? If it's the instruction is branch if equal, we know that it's a branch if equal from just the opcode. Okay, so from the opcode, it'll know, oh, this is a branch if equal. That means the ALU needs to perform a subtraction. So the main control unit will tell the ALU control unit that, hey, perform a subtraction, and the ALU control unit will tell the ALU to perform a subtraction. Now, if the instruction is, for example, an add instruction, then the opcode is not going to tell me that. The opcode will tell me, hey, this is an R-type instruction. But the add instruction and the subtract instruction, many other instructions, they all have the same opcode, which is 0. Okay? So when the controller finds out that this is an R-type instruction, then it's going to tell the ALU control unit, hey, this is an R-type instruction. Go take a look at what the funct field tells you and do that operation. And in this case, the ALU control unit will need the funct field. And where do we get the funct field from? So the funct field is going to be part of the instruction, and it's going to be the last 6 bits of the instruction, correct? And we already have these bits over here, right? The last bits of the instruction are down here. So we're going to take from these bits, we don't need 15 to 0, we just need 5 to 0. So we're going to take bits 5 to 0, these are the funct field, and we're going to pass these to the ALU control. Okay, and the ALU control unit is going to take a look at ALU op and the funct field if it needs it, and it's going to determine what the ALU operation should be, and it's going to pass that to the ALU. Okay, so that's what the ALU control unit does. Any questions? Is everything clear?
Sir, I noticed from the MIPS green card إنه الموقف is in our case opcode and the R when we are using the R format, it's either 0 or 1.
So the opcode when we use the R format is either 0 or 1. I don't have the sheet memorized, but yeah, there's when you use the R format, there's usually there's one value that for the opcode, and then the rest is we use the funct field to determine the operation.
Can't we use this very few options to lessen the hardware?
I don't understand how you want to lessen the hardware.
There's only like 2 options. I don't but we don't need to select because it's only 2.
I'm not sure I understand your question. So what we do when we have an R-type instruction is we specify the opcode corresponding to the R-type instructions, and we specify the funct field to determine what the operation is. So here the opcode is going to be provided to the main control unit. The main control unit is going to tell the ALU control unit that do what the funct field tells you, and then we're going to provide the funct field to the ALU control unit, and it'll process that and determine what the control signals for the ALU should be.
Oh, okay, clear.
That's how we use it. I'm not sure what other optimizations you have in mind.
Okay, thanks.
Yeah, you're welcome. Okay, so so having covered all of this, we have one more instruction that I promised you to talk about, and we haven't spoken about it yet. Who knows, who remembers what that instruction is? Jump, exactly. So we still have the jump instruction that we haven't talked about. So let's take a look at that. So jump instructions, we're actually not going to use most of this hardware that we have here, right? Because jump instructions, they don't access registers, they don't use the ALU, they don't access memory, they don't do any of this. So what does a jump instruction do? First of all, what format do jump instructions use? Right, the J format. Jump instructions use the J format. Looks like this. We have an opcode, and we have 26 bits, which are the address. And we use pseudo-direct jump addressing, which says that the jump address is going to be equal to the top 4 bits of PC+4, so bits 31 to 28 of PC+4, combined with the address, which is in these 26 bits here, times 4. Okay, so that's how pseudo-direct jump addressing works, and that is what we would like to do. What we would like to do is we would like to perform this operation over here to find the target of the jump instruction, and then select that as the next PC. So how do we do that? Well, first thing we want to do is we want to take the address and we want to multiply it by 4. Where do we get the address from? Right, exactly. It's bits 25 to 0 from the instruction. So the instruction is coming out of the instruction memory. So we're going to take 25 to 0 from the instruction, and we're going to multiply that by 4, or in other words, we're going to shift it left by 2. So now we multiply the address by 4. What do we want to do with this value? What do we do with the address after we multiply it by 4? We concatenate it with the most significant 4 bits of PC plus 4. So we already have PC plus 4 over here. So we're going to get 4 bits from PC plus 4, and we're going to combine those with the 28 bits that we got from doing the multiplication. Okay, so we're going to get 4 bits from PC plus 4, and we're going to combine those with the 28 bits we got after we multiplied the address by 4, and this will give us our jump address, a 32-bit address that we would like to jump to. Okay, so now that we have this address that we would like to jump to, what do we do with it? Right, we want to write it to the PC, right? But we can't just connect it to the PC because we only want to write it to the PC if it's a jump instruction. If it's not a jump instruction, we want to take the value that we have over here. If it is a jump instruction, we want to select the value we have over here. Okay, so you're absolutely right. We want to pass it to a mux. So we're going to have another mux over here. And what this mux is going to do is going to select we're going to use this mux to select either the result of the branch, either the target address of the jump instruction, or the target address we have from before, which is going to be either the target of the branch or PC plus 4. Okay, and what are we going to use to select the top value or the bottom value? When do we select the top value? Right, we select the top value when the instruction is a jump instruction. And who knows that this instruction is a jump instruction? Right, so my control unit knows that from looking at the opcode that this is a jump instruction. So we're going to take this and we're going to connect it to the control unit. We're going to have another signal coming out of the control unit called jump. Okay, and with this we have a full data path that supports all the instructions that we said we are going to support. Okay, now this control unit over here it's a logic block, right? The control unit, the main control unit, is a logic block. It takes in 6 bits, which are the opcode of the instruction, and it gives me a whole bunch of bits, which are the different control signals. So if I want to build this logic block, it's just a combinational logic block, and I just want a truth table, right, to extract what the various to specify what this block should be. And the table over here tells you, you know, for each instruction that we covered, what the opcode is. These are going to be the inputs to my logic block, and it tells you for each of the control signals that we have what the value should be. Okay, and I will leave it as an exercise for you to kind of go through this table and verify that each of these are correct. But for example, here the reg dest, for example, the reg dest, if you go back, you can see was supposed to be 0 when we are using RT as the destination, and 1 when we are using RD as the destination. That's exactly what we have over here. And when it's 1 for R-type instructions, because R-type instructions use RD as the destination, and it's 0 for add immediate and load word, because add immediate and load word use RT as the destination. And then it's don't care for store word, branch, and jump, because store word, branch, and jump don't write to the register, so we don't care which destination we select, because we're not going to write to the register file anyways. Okay, and you can kind of do the others on your own and make sure that you kind of understand the control signals for each of these different for each of the different instructions. Okay, we also have the ALU control unit, which takes 2 inputs: the ALU op, which is coming from the main control unit, and also the func field, and it has 1 output, which is the control signal of the ALU. And this table over here determines how the ALU control unit behaves. If the main control unit tells us, hey, this is look at the func field, we will look at the func field and do the corresponding operation. Okay, and if the ALU control unit tells us, hey, perform an add, for example, if we have a load instruction or a store instruction or an add immediate instruction, then the main control unit will determine what the operation is. Then we will just go do an add, and we ignore the func field. And if the ALU main control unit tells us, hey, do a subtraction, which is the case if we have our branch if equal, for example, then we just ignore the func field and we go and we do a subtraction. Okay? Any questions? Okay, so someone's asking, why do we need a new mux for the jump instruction? So we can have a 3-input mux, or we can have two 2-input muxes. It's here just kind of for the sake of explanation and showing you how we have the jump signal that controls this selection, we have the branch signal and the 0 that controls this selection. We've separated them into 2 separate muxes. Okay. You can also think of them as 1 mux that uses the combination of all these other control signals. Okay. Okay. Final note, just a quick comment about some performance issues. So the critical path here is the load instruction, right? Not all the logic blocks are used by all the instructions. The slowest instruction in the pipeline is the load instruction, because the load instruction has to go through the instruction memory. It has to read the register file. It has to use the ALU to calculate the address. It has to access the data memory to perform the load, and then it has to store the result back in the register file. Okay, write the result back to the register file. So the load instruction is the slowest instruction and it forms the critical path. So what we need to do is, when we pick the clock period, the clock cycle duration for our processor, the cycle must be long enough to for any instruction to execute. So the latency of the load instruction is what's going to determine the clock period of our processor. And what that means is that this is going to penalize other instructions, because an add instruction needs less time than a load, because an add instruction finishes when the ALU result is done. It doesn't have to go through the data memory. Okay? Or sorry, well, it can write back when the ALU is done, but obviously it has to write back. It's not done. But the add instruction uses less logic blocks. It takes less time. But because we need to have enough time for the load instruction, we're going to need to make the clock cycle long enough, and that way the add instruction, for example, will finish before the clock cycle is over. Okay, so one person is saying, why can't we break the load instruction into 2 cycles rather than 1 cycle, and that way the add instruction will not take as long? And that is a perfectly reasonable optimization that you can do. But we are going to do something even better. We're going to improve the performance of our processor by doing something called pipelining. And we will pipelining is a very important optimization, and all realistic processors use pipelining, and we will start talking about pipelining next time. So if you're interested in what we covered today, you can refer to section 4.4, and that is all for today, and I will see you next time. Bye, everyone.